Here we are at our 4.3 factoring a GCF set of notes. Now, the greatest common factor of two or more integers is the greatest number that is a factor of both of those integers. So, for example, if you had the numbers 12 and 30, just looking at those two values, the greatest common number that you can pull out of both of those is 6. 6 goes into 12 evenly, so does 30. So 6 also goes into 30 evenly. And as a result, that's the biggest thing that if you were to try and pull out of both numbers, that would be your GCF. Now, to kind of help illustrate this idea of a GCF in factoring, I want to go ahead and go back to distributing items because we've done a lot of that in the past. So, for example, here you have 3 times the quantity x plus 2. We know that if we go ahead and distribute, we would have 3 times x giving you 3x, and then 3 times 2 giving you positive 6. Okay? And so the idea is for distributing, you're multiplying things in, whereas when you're factoring, that I often reference as anti-distributing. You're pretty much just doing the opposite. So imagine then if you started with the 3x plus 6, what number can you pull out of both of those two values? Well, in this case, their GCF is 3. They both share a common factor of 3. Now, this doesn't just have to happen with numbers. You can also apply this with variables and other values too. So, for example, here, if we were to go ahead and distribute x, you'd end up with x times x is x squared. And x times negative 7, we get that negative 7x. Now, if we were to work in backwards, we're looking at x squared and negative 7x. We both notice that they both share a common factor of x. This guy does not share any kind of factor of a 7, so we can't really pull that out. And as a result, our GCF then is, in fact, the x variable itself. And so when you pull out an x out of both terms, you're left then with this x minus 7 inside the parentheses. And again, here's another example where you can distribute kind of numbers and variables. So here, if we were to distribute 6x into 2x, that would give you 12x squared. And then 6x times 1 gives you that 6x. Now imagine working backwards, starting off with 12x squared and positive 6x. Well, we know that they both share a common factor of 6, so you could pull that out. As well as they both share a common factor of the x. Notice how they both have x. So we can pull that out as well. And so when you do that, you're left then with that. What I often reference is what times that 6x gets us that 12x squared. Well, 2x would have to be that value. Likewise, if we took our 6x and we pulled a 6x out of that, or in other words, what times your 6x gets you that 6x, it would have to actually just be a value of 1 acting as a placeholder. Okay, so now let's go ahead and use this in action when we see it with example 1. So here we have we're asked to factor the expression using the greatest common factor. So what's the biggest thing we can pull out of both of these terms here when we look at 9a and 18? Well, notice how they're saying that we pulled out a 9. That is the greatest common number between 9a and 18. And so if we were to pull a 9 out of there, then what times 9 gives us that original 9a? That's what you'd have to ask yourself. 1a accomplishes that. So that would be, you can almost imagine it like you're dividing it by 9. But you're not solving, you're just pulling it out of that term. Likewise, if you were to factor out a 9 from 18, you'd be left with 2 there. So that's why we have a positive 2. Now when we look at our second one, we're looking at 7x squared and negative 14x. The biggest number that you can pull out of both would be a 7. And notice how they also both share that x term. You can pull that out as well. And so that's actually what we end up with. We pull out a 7x from both terms. Now we're asked to find out what is in that blank spot for that. Well, we're asking ourselves what times that 7x gets us that 7x squared first term. 1x would have to be that value. Again, you're kind of just dividing that 7x when you factor it. And then likewise, if you pull the 7x from our 14x, then we would have a -2 there, and we do. Looking at the third one, looking at 12x and positive 80x squared. Well, they both share a common factor of 4. So you would imagine pulling a 4 out. As well as you notice how they both share an x, so you can pull an x out as well. Now asking yourself, what times that 4x on the outside gets us this 80x squared term that we're looking for? Well, 20x would accomplish that. So that's what we're going to put inside of our parentheses. And then finally, our last one. We have 4x y to the third plus 16x squared y squared. So you can have multiple variables in this process too. But again, the game is still the same. You're looking and you're asking yourself, what can I pull out of both of those that they both share? Well, they're both divisible by 4. So we can factor out a 4. Notice how they both have x. Now here's the thing. This guy has x to the first power. This guy, on the other hand, has x squared. Now you can only pull an x to the 1, and the reason for that is this first term only has 1 to give. So you can't pull stuff out of something if it's not there yet. And that's why we can only pull a greatest common factor for x there. In terms of our y values, we can also pull out, they both share y, but the biggest amount that they have and share, like this has y cubed, this has y squared, the biggest amount that they both have would be y squared, because that's this term doesn't have any more y's to be able to give. So we could pull out a y squared there. And so when we do that, that is our GCF. This would be that leftover stuff from the things that we pulled this 4xy squared. Okay, and you can always check and see by distributing just to make sure, hey, you got this correct or not. But again, though, that is example 1 from our 4.3 set of notes.